Okay, so this is first example of the induction motor. A three-phase 100 horsepower, 460 volt, 4-pole 60 Hz induction machine delivers rated output power at slip of 0.05. Okay, determine the sebenarnya semua A, B, C, D, F lah. Okay, determine the A synchronous speed and motor speed. Synchronous speed and motor speed. Just now we know the formula for synchronous speed, right? What is formula for synchronous speed? Here, here this formula for synchronous speed. 120 F divided by P. So 120 multiplied F. F is given there is 60 Hertz. Divide P. P number of pole, right? So in this case, how much number of pole? 4 pole. So divide by 4. Alright. So we have an S equal to 1,800 RPM, right? This is 100 RPM. You want to find in the Hertz, you just divide by 60 only, yeah? 1,800 RPM divided by 60, we got unit in Hertz. That means we can define synchronous speed also in Hertz or in radian per second. Unit. So the conversion you must be know to use. You want to get radian per second. So this RPM multiplied by 2 pi divided by 60. We got unit in radian per second. You want to find it in Hertz, just divide RPM divided by 60. Then you straightly you got in Hertz. So the conversion of unit you must be not familiar lah. Don't just start in one unit only. You can use in Hertz, you can use in RPM, or you can use in the radian per second. Okay, motor speed. Motor speed just tadilah kita ada formula just now. Where's formula motor speed just now? Here. 1 minus S multiplied by omega S. Slip given already, which is 0.05. Omega S, just now we calculate just now 1,800. Then we got the in the RPM 17110, or in Hertz 28.5, or in radian per second. This value lah. Okay, 178.98. So today you familiar with this unit. Later on you see the unit, easily you can convert from RPM to Hertz, from RPM to radian per second, and the other way around. Right. So I think hopefully it will give you many knowledge today, especially to get the correct unit for the speed, for example. Okay, fine. So NS and R done already. I just go briefly lah here. The speed of rotating air gap field. What is the speed of rotating air gap field? This one equal to synchronous speed. Same. When they say rotating air gap speed is rotating magnetic field lah. Same. RMF. So equal to omega S. Okay, so air gap speed equal to synchronous speed equal to NS equal to 1,000. So the name for that lah. Sometimes they call it synchronous speed. Sometimes they call it air gap speed. You know that one. I mean the speed in the air gap equal to NS. Equal to this formula lah. Alright. Frequency of rotor current. Okay, so we know that in the AC machine we have current in the stator, and we also have AC current in the rotor. Okay, when the current flowing in the rotor, we have rotor frequency. Okay, we got stator frequency and we got rotor frequency. So rotor frequency what is determined by the shown by the F2, the symbol lah. So F2 is equal to S multiplied by F1. Okay, so if we have F1 equal to just now 60, this is our the frequency of the stator, 60 Hertz. So the frequency of rotor you have to multiply by S. Then in the rotor side we have the frequency of 3 Hertz only. So very slow frequency compared to the stator part. Because rotor also carries AC current. So this is the frequency for rotor. Okay, simple je lah, just multiply by S. F1 tadi, 60 Hz ni divide by S. That give the frequency rotor. Slip. Frequency, what is slip? This is all, basically this example more on definition. Slip. Slip is the difference between rotor speed and synchronous speed. Okay, this formula lah. So slip speed equal to slip frequency, same. You can say slip frequency or you can say speed equal to NS minus NR. Or S and S lah. Equal to, you just minus lah. You just minus 1,800 here minus 17110. You got 80 lah. 90 RPM. in RPM lah. Just deduct, you just deduct WS or NS minus NR, or S multiplied by NS lah, same thing. So it can be determined by RPM or radian per second. You can change the unit lah. You want to change the unit, you just change the unit only. But when we talk about slip speed, is different between synchronous speed and rotor speed. Okay, that's these three A, B, C, D is very important definition for the induction motor lah. Number E ni the speed of the rotor relative to the rotor structure, stator structure, and also stator rotating field. What is the speed relative to this thing? Then you have to answer this one lah. Rotor, the speed of the rotor field relative to the rotor structure is 90 Hz, 90 RPM. It's slip speed lah, call it. And this one. Okay, that one can see your own. Okay, hopefully you can understand briefly on the basic thing about calculation about the thing. So A, B, C, D ni is very important parameter that you need to know in induction motor. Okay, we normally ask you what A, B, C, D lah. E and F ni we don't know. We don't ask you actually. Alright, so now we go to this. You just follow this slide lah. Equivalent circuit. We have done this one before in the previous slide. Okay, we know that we have stator and we got rotor. Rotor is short circuit like that. And the rotor depending on the stator, depending on the winding lah. Sometimes we have this is star connected system. Sometimes we have delta. Sometimes we have star. Sometimes we have delta, depending on what kind of machine we connect lah. So we have two machines. So in order to study analyze the machine, we need to find the equivalent circuit. We have done before in the previous slide. Sometimes I just skip only. I don't want to repeat. This is stator part. We have done before. We got V1 equal to I1 multiplied R1 plus I1 multiplied by GS1 plus EAG. And here they use symbol E1 only, but it's equal to EAG lah. Voltage induced at the, or you call it back EMF of the stator. Same thing like we did before. And the I flux stands for the magnetizing current. This is a magnetizing current. The current that used to set up flux in the induction motor. That is meaning by the magnetizing current. So the flux in the machine is set up by this I flux there, or you call it magnetizing current. I flux combination of IM plus IC lah. I flux ni. IM stands for magnetizing current, which the current that we use to set up the flux lah. IC represent for the core loss. You know the core, machine got the core, so we have core loss there in terms of heat. So that one represented by RC. So IC square RC give you the core loss. Okay. So in this induction machine, basically the IM here, magnetizing current, contribute about 20% to 50% of stator current. The amount of current that IM there is about 20 to 50% of this I1. Okay. Whereas in the transformer, it's about 1 to 5% only. But if you compare transformer, the IM there is about 1 to 5%. Small current required in the transformer. But in the machine, we need high current to set up flux there. Okay, because machine has the air gap. Air gap there. That's why we need to have more current to set up to overcome this thing there. That's why the current is about 50% to 50% of the stator current. Understand? Kalau if your stator current, for example, 1 ampere, that means it's about 0.5 amps required there lah to set up flux in the machine. Okay, and X1 there normally for the machine, X1 is larger than transformer. X1 here, because basically machine and transformer same structure, right? In transformer we got the primary winding and secondary winding, right? In transformer, but in transformer both use same frequency. In the primary use F1, in the secondary also F1. But in our AC machine, induction motor is different. Induction motor we got stator and we got rotor. But we have rotational part there. That's why frequency is different. Okay, it's not like transformer, same frequency. Transformer is stationary device. Okay, it doesn't move. But motor is a rotational device. That's why frequency F1 is frequency at the stator is not equal to frequency of the rotor. Okay, so but if you compare transformer and the motor, S1 in the machine here is larger than and then transformer in the S1 in the transformer lah. Get some knowledge lah. You want to compare that. Okay, this is rotor side. This is stator side just now. This is stator side, and this air gap lah, air gap voltage, and this is rotor side. And as we mentioned before lah, rotor current given by E2 divided by this one lah. Then we got SX2 because we have different frequency in the rotor side. We got F2 there, where F2 to SF1. That's why you multiply by S there. Okay, that's why you got slip there because F2 to SF1. So the inductor will become SX2. Okay, this one we not touched already in our last lecture. So I just show only the equation for the primary one, and this primary voltage V1 equal to R1 plus I1 plus JX1 I1 plus back EMF. And this is rotor equation. So as done before in the last lecture, I just show you only here. And then some slide need to skip only lah. Okay, this is circuit that we have. When we combine both primer and secondary, we have this one lah. We got the circuit. Okay, all right. You see this circuit now. We have R1, X1, and this is your air gap there, and this is SM, RC. RC normally is a core loss where we can remove from here lah. We can remove from here, then we can embed it the core loss into the mechanical loss because core loss is fixed. It's fixed. It does not change. It's fixed. I mean, even though the current change, even the stator current change, for example, the RC loss is constant. That's why you can remove this component and you can embed it to the rotational loss in the mechanical loss. Okay, and that's your SM. This your stator current. This your IM, which represent the magnetic current, like we showed you last previously lah. And A stand for A, as I mentioned before, is a turn ratio here. So normally in machine we say that turn ratio equal to 1. So does not make any problem. And then you got X2 and R2, and this one you can break by 2 as I mentioned before lah. So R2 over S ni, previously you got R2 over S there, right? This R2 over S there. You can break to 2 part lah. R2 plus R2 over S, 1 minus S. So this R2 over S ni can be represented by R2 plus this portion lah. Okay, this one. And as I mentioned before, R2 represent the core loss, core loss in the rotor. Core loss lah, winding loss or copper loss in the rotor. And then this one represent the mechanical power. I squared lah. I squared R2 represent rotor copper loss or rotor winding loss, and I2 squared multiplied by this component represent the mechanical power, gross mechanical power that we need to rotate the machine to produce the mechanical power. So basically this slide is similar like we had before lah, just some extra explanation only. Hopefully you can grasp it. This formula that air gap power. Okay, air gap power equal to PAG as we did before. So PAG is the power that we transfer from the stator to rotor. So equal to I squared R2 over S. And this R2 over S can be break to this 2 part. And this one equal to P2 plus P mechanical lah. P2 stand for what? Stand for the rotor copper loss. Equal to I2 squared R2 or SPAG. As I mentioned before, equal to SPAG. And P mechanical equal to I squared multiplied by this one equal to 1 minus SP PAG. Okay, that's what just to emphasize back the one that we studied in previous lecture, just so you can have some you can refresh back your knowledge. All right, this one just ratio only, that's better. Okay, now we have another example there. Example number 2. A 3-phase 15 horsepower. You know horsepower, Horsepower is rated for the machine. Normally for the machine, electrical machine, we rated as horsepower. So 1 horsepower equal to 746 watt. Dia punya ratio, 1 horsepower to 746 watt. So you multiply lah 15 by 740 watt, then you can get the power in watts. So that is the relationship between horsepower and watts. So each horsepower equal to 486 watts. Dia punya power dia. 460 volt voltage line to line. This is voltage line to line. 4 poles and 60 hertz. This is speed of induction motor, 1728 RPM. Delivers full output power to a load connected to its shaft. Okay, the windage and friction loss of the motor is 750 watts. Determine the mechanical power, how much mechanical power developed by the machine, how much the aggregate power, PAG. You should know the symbol when you start the mechanical power, PM lah. Then PAG lah, aggregate power. And rotor couple loss, which is P2. Okay, understand? So what is the power here? 15 horsepower is a net power. This is output power, net power that having by the machine. This meaning by 15 horsepower. The net power that produced by the machine. Okay. PM is a gross power, gross mechanical power. Okay, now we... Alright. Okay, find the full shaft power first. Full shaft power, you need to find the 746 multiplied by 15 horsepower just now, which is 11,190 watt. This is a net power, or you call it full shaft power lah. Net power. And then mechanical power equal to what? Equal to shaft power plus rotational loss. This represents PM. Mechanical power tu is combination of shaft power plus mechanical loss, rotational loss lah. So 190 plus 750 just now. Yeah, this is losses in the mechanical. So you got the P mechanical there. So in your P mechanical must be bigger than P shaft lah. If you find something different way, that is wrong. P mechanical is a gross power. So gross power means net power plus rotational loss. So 11940 is a PM, or gross mechanical power. Okay, then find the synchronous speed. From the data we have here, we can find the synchronous speed, which is NS 150F. I use the RPM there. You can use any speed that you like lah. But common for my notes, normally I use this way to present the NS. Okay, 120F. F is how much? 60. Divided by P. O, number of poles is 4. Then you have the synchronous speed in this machine, 100,000. And then you can find slip, operating slip. Or you call it the full load slip or rated slip. Same thing lah. Because why you say that? Because the speed is at rated condition. This is full power. This means the rated condition. The 1728 is a rated speed of the machine. So you can find the slip then, because you know the rated speed already. Then you can find the slip. This slip, you call it the rated slip lah. Rated slip. So 1,800 minus 1,728 divided by 1,800. This is 0.04 or 4% is rated slip. Alright. And the slip speed, how much slip speed? Slip speed just minus lah. That means we have here 72 RPM. This one minus this one, the top one. 1,800 minus this, you got the slip speed, which is 72 RPM. And this is slip 4% or 0.04. And then you're going to find PAG now. What is the relationship with PAG and PM? And just now you know, right? PM equal to 1 minus SPAG. PM equal to 1 minus SPAG. So PAG equal to 1 PM divided by 1 minus S lah. So PM, P mechanical, you know already here, 11940 divided by 1 minus 0.4. Then you got this aggregate power. And then later on you can find the rotor copper loss, or P2, just SPAG. So when you know the PAG, you know the S already, then you can find the rotor copper loss, which is P2. Okay, clear? So that's how we calculate some parameter related to the machine here lah. Okay, when we given the rated condition. This is a nameplate of the machine. When you buy a machine, you have this kind of data lah. 15 horsepower, and this line voltage, number of pole, right? operating frequency, rated speed, and this one is given dah. They said that the losses in the mechanical loss go to 750. Okay, I think that should be clear lah. And you can familiarize all the formula now. What formula we studied before, you already familiarized with that. Alright, now we go to the equivalent circuit. I just follow this one lah. Equivalent circuit ni, this is the original one just now. You have RC, but because as mentioned before, RC ni is a losses in the core of the machine, okay, and it's constant. Whatever load change, it doesn't change losses in the core itself. So you can remove RC lah. You can remove RC. You just left SM only. So also all the losses in the RC will be included, embedded in the core loss or mechanical loss there. This we call it the approximate circuit. Okay, approximate circuit, which this RTPE circuit that we studied in previous lecture. So what is different with this one? What is different? The X here. So here you got X in the middle, but here the XM you can move in front. So that EAG or E1 equal to V terminal, V1, same. Here you bring SM toward here. So V1 equal to E1, E1 or EAG, same thing lah. So easy lah for us. If you do that, I mean you can have parallel circuit now. Here you got series parallel, right? But here you got parallel circuit only. So you can find easily the current there. I1 equal to IM plus I roto. Simple equation for the current. I1 equal to IM plus I2, I roto lah. So what is IM? Just V1 divided by GSM, straightforward. What is the I2? V1 divided by this impedance. So you can get directly the rotor current, and after that you can directly find the stator current. So stator current I1 equal to IM plus vector. You have to add in the vector. You tak boleh campur the numbers. You see the vector. They got angle and amplitude. You have to add the vector together lah. It's complex number. So IM equal to I1 equal to IM plus I2. So this one simple lah for us. But here you need to do, you want to find the I2, you need to do current divider, or maybe you need to get the total impedance first lah. Get the total impedance first, and then you can find I1. But again, you need to check the question they ask you. Don't ask based on your feeling. You need to check your things. 1 second. Alright, so based on this diagram, so whether you want to use IEEE or this circuit, again you need to check the question the question they ask you to. If they ask you to use approximate, then use approximate lah. Approximate, use this one, not this one. RC is not there. We don't give you the data for RC, so we never will give you SM only. So use this one. Or IEEE. So again, I mentioned to you, if they give you IEEE, so the best way you have to find the total impedance first lah. This one series, parallel, and series. We do like that. Get the series circuit first, impedance for series, S2 and R2. When you have X, don't forget about J, because these are imaginary numbers. Okay, so that means you got JS2, series dengan R2 over S, parallel dengan GSM. So get this impedance first. and then add with this series. And then you got total impedance lah. So you got total impedance. So V divided by total impedance give you the stator current I1. You want to find the I2, then you need to use current divider. I think all of you know the current divider. So little bit complex lah, but it's okay, still can be used. So the best circuit to solve is this one lah, approximate. But again, as mentioned to you, depend on the what they ask you in the exercise later on lah. But in the exam normally we say clearly lah, use this circuit or use this circuit. So easy lah. So you have to follow the instruction. Alright, so this IEEE circuit, as mentioned before lah in the previous last lecture, yesterday lecture. So okay, and then from this circuit also we can deduce the other circuit. We call it Thevenin. I think I will know. I will really familiar with Thevenin. What is Thevenin circuit? So you got the IEEE. You will need to find the voltage across SM. Using you take out this one first. You take out the rotor part. You remove the S1 and R2 over S. Remove first. Then find the voltage across SM using voltage divider theorem lah. I think everybody know voltage divider theorem. So V1 divided by impedance here multiplied by SM. That give you the voltage across SM, which is voltage Thevenin. So this V Thevenin lah. V Thevenin is equal to voltage across SM. And then after that, because you need, in order to find Z Thevenin, you need to short all the sources there. So in this circuit, we have voltage source. So how to make it the source zero? Sorry, you need to make it the sources become zero, not short. The voltage you need to short, okay? And if you got the current, you need to do open. But in this circuit, we have got voltage. That means you have to short this terminal. Then see from this point. You see from this point, meaning that you see the GSM parallel with this XM and R1. So R1 and GS1 is series parallel with the GSM. Then you have this component for Thevenin circuit, Thevenin impedance. Then you construct the Thevenin circuit there like that. This will be Thevenin. So Z Thevenin can be divided by 2R Thevenin plus X Thevenin, and after you put the component for the rotor. That you call it the Thevenin circuit. So you need some extra work lah. Okay, but the things here, if you use Thevenin circuit, okay, what is the drawback of Thevenin circuit? Thevenin circuit basically same like IEEE, but IEEE is a series parallel, right? Thevenin is series circuit only, so you can get the component same thing. But the problem here, you only have I2 only. If you use Thevenin, you only have I2, which is rotor current only. You cannot get the stator current there. Okay, because I2 is series with this component. That means if we use Thevenin circuit, we only can measure the I2. From I2, we can find the power lah. You can find the power. From the power, you can find the torque. Okay. So basically, Thevenin can give you the current, give you the power, give you the torque. Alright. But it does not give you the stator current. That means you don't have stator current, you cannot find the efficiency. If you got efficiency, you need to find the stator current, right? You need to find the input power. Input power requires stator current. So if they ask you to find the like efficiency and so on, definitely you cannot use Thevenin circuit lah. You need to use this circuit just now, IEEE lah. You cannot simplify this one. So I found some of you, even though we are not construct you using Thevenin, but I found a few of you they still like use Thevenin circuit. If the answer is correct, fine lah, doesn't matter. But as I mentioned just now, it only give you the I2 only. From I2 you can get power. Why you got power is, yeah, you see the formula power just now. Where is formula for the power? Here. This power, PAG, PEG equal to I2 squared. That means you can find the power there. Power PAG. Or I get power lah. You can find the power for the rotor side if you know the I2. So I2 gives you the power. When you know the power, you can find the torque. Because the formula for torque is equal to, tadi formula dia. Ada sini. Okay, this different slide. Torque equal to power divided by speed, right? As I mentioned you previously. Torque equal to power divided by speed. So you know the power already, PAG you know. Divided by omega S, you got the torque. So Thevenin circuit can give you the torque, can give you the power. But it cannot give you the efficiency. Because efficiency, you need to know the stator current. So that's the thing lah. So if they ask you to find efficiency, then definitely you need to use this IEEE or approximate circuit. Understand? So hopefully you don't start there lah. So we have some knowledge already lah. The importance of circuit there. Thevenin, okay, you can Thevenin is just simplification of this IEEE only. So basically it performs same like IEEE. Same thing, only we simplify from circuit like that. This circuit series parallel becomes series circuit only. Like that. And then we know that just now you can find the I2 from there. I2 just V Thevenin divided by impedance lah. I2 just V Thevenin, you know to V Thevenin, you divide by impedance there. We got the I2 rotor current. So once you get the rotor current, we can find the power, PAG, you can find the PM, everything lah. You can find the power and you can find the torque. That's the thing that you can calculate from this Thevenin circuit. But unfortunately, it cannot give you the stator current. So because you don't have stator current, you can't calculate the efficiency. Because efficiency need to find the P out over P in, where P in equal to square root 3 V line I line. I line equal to I stator. Okay. So here you cannot find the stator current punya data lah. It's not sure. It's not impossible to find stator current there. You only can find the rotor current. That's my discussion. My knowledge give to you lah. You need to have some something that you see the circuit, you know already. Oh, this can be used. This one cannot be used like that. So okay, so this is Thevenin. Thevenin is simplification of IEEE. It can be used to calculate the power, can use to calculate the current, rotor current, and so on. But it can't give you the stator current, and it can't give you the power factor, because stator current gives you the power factor. So without stator current, you don't know the power factor, right? That's the issue. Okay, this is a formula for Thevenin just now lah. Same thing I mentioned. You just V1 divided by the total impedance, impedance of R1, GS1 and GSM, and then multiply by GSM. That gives you the V Thevenin. And then Z Thevenin, as I mentioned before lah, you remove this part, remove first, and you see from this point, and all the sources must be 0. Okay, everybody know about the Thevenin circuit. So then, because we have voltage source, so we need to short circuit. Short circuit means we make it voltage equal to 0. Then we see from this point. So from this point, we see that GSM parallel with this component. Then we can find the Z Thevenin. The Z Thevenin is combination of R Thevenin and X Thevenin. That's simple thing lah. Alright, any question? Okay, clear? Okay. So we have circuit now. Now our job now to find the component for the circuit. Component for IEEE or whatever lah. This one. We need to find the R1, S1, SM, S2 and R2 now. So we have to do testing. We have to do testing as we did in the lab machine. Okay. So we have to test that need to be carried out in the lab. First, we need to test, we call it, in order to find the equivalent circuit, we need to do two tests. First, we call it the no-load test, and the second one is a block rotor test. So two tests that we need to be done. If you buy a induction motor, okay, if the supplier didn't give any data sheet or anything they give to you, then you need to do testing lah. So from these two testing, we can work out the component for the induction motor. So what is a no-load test? What is no-load test? No-load test, we run our motor. So we run our motor, induction motor. We must supply the motor with the rated voltage. One rated voltage and rated frequency condition. So you need to apply voltage. For example, normally in Malaysia lah, we have voltage 415 volt. This is a 3-phase voltage. We need to apply line to line 415 volt, and then frequency is 50 hertz. And make sure that your shaft, induction motor shaft, is not connected to anything lah. Just free running. You don't connect to any load. It's free running. So you supply voltage for one file with frequency 50 Hz, and you do the measurement. What is the measurement you need to do? The power, no load power, how much the power machine consume during no load. Then you measure the current, how much the no load current in the stator winding, and how much the power factor and so on. Normally we use the power meter. So in the power meter, then for example, we use fluke power meter, so we can see everything there. They show you the voltage, the power factor, the VAS, and so on. You can get from that measurement. Okay. Understand? That's a no load test lah. So not the no load test. Alright, so I go back to this circuit here. This is circuit just now, right? What happened during no load test? If you see the equation for the slip, yeah, this is slip equation, right? Ns minus Nr over N. During no load test, normally the rotor speed here, Nr, the speed of rotor ni, very, very high and very, very close to Ns. For example, Ns here is 1,800 RPM, right? So Nr very close, maybe 1785 or 1790 like that lah, very close. That is the rotor speed during no load test. So because of that, so Ns minus Nr equal to 0 lah. So 0 divided by Ns becomes 0. So slip equal to 0 during no load test. Clear? Why? Because rotor speed very, very close to synchronous speed. So that means that the slip equal to 0 during no load test. So if slip equal to 0, then you go back to the circuit just now. Please come. Okay, here this is the circuit that we have previously. So in this branch, the right branch there, we have R2 over S. Basically, we have R2 over S. R2 over S there. So because S is a 0, then something divided by 0, it becomes infinity. Correct? Infinity, very high impedance. So infinity means this branch become open circuit. Infinity means very high impedance lah. So high impedance means the system become open circuit. Open circuit means high impedance. Current cannot flow lah. High impedance means the current cannot flow. So the circuit look like open. That means you got the right branch become open circuit. So what happened to our circuit now? It behave like this one. This circuit we have when during no load test. RC we remove lah. We see RC is not easy. We already embedded in the mechanical loss, so we have SM only. So this circuit happen when we do the no load test. That means we can calculate the S1 and SM lah. So from voltage, we know we measure the voltage. We know the current. So V divided by I, you got the Z total lah. Z total. Okay, Z total. And then we know the power also. No load power. So from no load power, we can find the no load resistance. Total no load resistance. So you got we know the Z, we know the no load resistance, then we can find the X. So X Z squared minus R squared square root 2 equal to S1 plus SM. That is information that we can get from the no load test. Yeah. R1 is impedance that we measure resistance of stator that we measure using the multimeter only. You use multimeter, you can find R1 easily lah. But in order to find X, you need to find Z. Z is just V divided by I. V divided by I got Z. So Z squared minus R squared, not this R no load. From you know the power when we do the measurement, we measure the power consumed by the load during no load test. So that power, from that power, the power to I squared R, then you can find R no load. So R no load, so Z squared minus R no load squared, square root 2, gives us the S1 plus SM. That is condition. So as mentioned there lah. Exciting current, I flat just now lah, rotational loss. Rotational loss means during your no load test. No load test means rotational loss consumed by the machine. The power that consumed by the machine basically is used to supply for the rotational loss. That is for the no load test. Okay, so we have this circuit, equivalent circuit for the no load test. Now, the second test is block rotor test. What is block rotor test? Block rotor test is a test that we carry out to find the component for the R2, X1, and S2 also. Okay, so we need to block the rotor. So you have to lock the rotor first. If we have mechanical device there, you lock the rotor. And then you increase the voltage slowly by using variacs. In this lab, we have variacs. Variac is a kind of auto transformer lah. So you can change the voltage steadily from 0 to rated value by using variac, and then measure the current. You measure the current, and you must make sure that the current is not exceeded the rated current. You know that if in the lab machine there, if you remember, the rated current is 10.9 ampere. 10.9 ampere. So you need to increase the voltage slowly, steadily, up to 10.9 ampere only. Cannot go beyond that. Otherwise, your conductor become very hot. You can smell the hot. Current very high. I square R. So losses very high during that time. So you lock the rotor speed equal to 0. So increase voltage up to the rated current and do the measurement lah. We measure the voltage, how much during rated current flow, how much the rated current, how much the power consumed, how much the power factor, and so on lah. That one can be obtained from the meter, from the power meter that we connect to the system. Okay, that is meaning by block rotor test. And then also depend on machine. If the machine bigger than 10 horsepower, 20 horsepower, for example, then you need to use frequency 25% of rated frequency. Understand? If your rated frequency is 60 Hertz, that means you need to apply frequency of 15 Hertz during this test. That means you need to use inverter lah. You must have inverter lah. Without inverter, you cannot change the frequency. So that's one used for the high power machine. For the low power machine, we don't need to change the frequency for the lab. For example, in our lab machine, we just use same frequency with 50 Hertz only, because the power rating is less than 20 horsepower. Okay, so that's how the condition. We need to change the frequency 25% of rated. Then we increase the voltage up to the rated current, and then we take the measurement. Okay, if you see this circuit just now, here, right, this circuit, during block rotor test, as I mentioned just now, block rotor test NR equal to 0. If we ask you how much speed of the rotor during block rotor test, of course 0 lah, sebab you block kan. So NR equal to 0. And S equal to 1. S equal to 1 lah. Okay, S equal to 1. So here, you see this branch there, right branch there, R2 over S, S equal to 1. So equal to R2 lah kan. R2 over S, R2 over 1 equal to R2. So R2 ni, compared dengan SM ni, much lower the impedance kat sini lah. Impedance of the right branch ni, much lower than SM punya impedance. So what happened is, since that the current sees that this branch look like open circuit. Open circuit. That means all the current will flow through R1, X2, and R2 over S. So this one look open circuit because impedance here very high compared to the here. You know the current, right? The current goes for the low impedance kan. Kalau you short something, all the current will flow to the short circuit wire. Why? Because it's low impedance. This is a characteristic of current, right? They try to find the lowest impedance lah. Itu characteristic. Everybody must know that lah. You short something, the current will flow to the shorted wire. Because of what? Because of low impedance. So similar here lah, because R2 over S equal to R2. So this one very low impedance compared dengan SM punya impedance. So that's why we have this circuit. This circuit, approximate circuit during block rotor test. That means we got R1, X1, X2, and R2. Okay. So from here, we can calculate the component. So we first find the Z total impedance. So Z equal to V1 divided by I1. V1, you know how much voltage that you apply during rated current. and then you divide by I1. So you got the Z block rotor lah. And then you can find the power. Power during block rotor test. We have the block rotor test also consume power. So we can find the power. We can find the resistance, total resistance lah. Where total resistance in this test equal to R1 plus R2. R1 plus R2 equal to total resistance. Then after that you can find the R2 easily lah. You know R1 already. You can find R2. So the test will give you the R2. R2 is rotor resistance, remember. Okay. Then you know the Z already. So Z squared minus R block rotor square root 2 give you the X. The reactance, which is S1 plus S2. And then you can find the S1, S2. Just like that. And after that, you get the complete circuit. You get from here, you got component for the SM, S1. Then here you got component for this one. Then after that, you can construct the circuit, which is equal to this one lah. You can equal to this circuit. You got the complete circuit for your induction motor now. So once you got this circuit with the component at R1, S1, you got the component already, SM, S2, and R2. This you call it the per phase. Remember, per phase IEEE recommended equivalent circuit. Per fasa, okay, per phase. Then you can solve your problem. Okay, you can check how much your motor efficiency, how much your starting torque, how much the power, everything lah that related to the machine, induction machine, you can easily assess. Okay,